Right. Hello, everyone. Welcome to the Scala meetup or INNOQ offices. We will have two talks today. First one is by Daniel, who came all the way from Berlin to visit our beautiful office here in Munich. And he's going to talk about mutation testing. And afterwards, we will have a short break where you can grab some more of the leftover pizza. And don't take all of it, though. We have promised one of our colleagues who couldn't be here today that he can get some less. You didn't promise? Okay, then take all of it. Of course, some drinks. And then the talk after that will be mine. But first of all, let's give a big round of applause to Daniel for mutation testing.
Yeah, thank you. Hello, everyone, and welcome to my talk on testing in the post-apocalyptic future. So, of course, as Scala developers, many of us think that we can encode everything in types, so we don't really need to test a lot. But this talk is for people who think that even though we have such a strong and powerful type system, having a powerful and strong test suite is really important. So in this talk, I want to talk about a technique called mutation testing, but also about how this technique relates to other techniques of testing, for example, property-based testing, which Lars will give a more detailed talk about afterwards. So, what is a strong test suite? Well, for some people, code coverage is a good metric for the quality of a test suite. So the higher the coverage of our code, the stronger our test suite. So high code coverage would mean that we are relatively sure that we have a high quality software. And of course, some people also establish a quality gate in their build pipeline so that the build will fail if a certain code coverage threshold isn't met. Well, let's have a look at an example function and what code coverage really means. So this function, non-negative, checks if a given integer value is non-negative or not. It's pretty simple. And if we want to have 100% branch coverage, then we need to provide at least these 3 test cases. So with these 3 test cases, we achieve 100% branch coverage, which means that all of the branches in our function under test are actually covered by our tests. Okay, so in Scala, branching happens mostly via if expressions or pattern matching expressions, as we saw in the example function where I used an if expression. But here's the interesting thing. If I take away 2 of the test cases, then I still have 100% branch coverage for my example function. And I can even leave out the assertions altogether. So in this case, we still have 100% coverage. But the test, of course, is completely meaningless because it can never fail, because there aren't any assertions. So code coverage doesn't really care about your assertions and whether they're actually meaningful. All that matters is that the code has been executed. So apparently code coverage is not really a good metric for a strong test suite. We have seen that we can have really bad tests without any meaningful assertion and still get a high code coverage metric. So what are the characteristics of a strong test suite that we should aim for? Well, of course, we should actually have assertions, and then we should not just test the happy part, but also all of the corner cases that we can think of. And now I want to talk about some tools that actually help us ensure that we deliver high quality software, because code coverage is not really one of them. So one of the tools that has become very popular in functional programming, but even in other paradigms, I mean, there are property-based testing frameworks for Java now. So compared to traditional unit testing, property-based testing has a pretty different approach because it requires a completely different way of thinking about the function under test. And also a completely different way of writing the tests, as we will see. So here we have another function, non-negative ratio, which computes the ratio for a given list of integers, the ratio of values that are non-negative. So in traditional unit testing, we would need to come up with a few examples to test our function. So here we have 3 such examples, which, of course, they are pretty arbitrary, and we try to cover all of the different cases that we can think of. And in property-based testing, instead of examples, we have to think about general properties of the function under test. So in this example, I came up with a property that the ratios of a given list of integer numbers and the ratio for the inverted numbers adds up to 100 using an invert function, which you can see here. So what this does is the testing library basically generates test cases for us using random values. We just specify that we need a list of integers, and then we will get a lot of different test cases with different lists of integers. And if we have this, usually all of the corner cases will be covered. And I think the biggest strength of property-based testing is that it can uncover gaps in our implementation by coming up with these random values that we didn't think of when we specified examples. And this is, of course, also what happens in this example, because we didn't think of the case of an empty list. So when we run this property test from the previous slide, we will get this arithmetic exception, division undefined. And here we'll see the input value, the empty list. Okay, so apparently our implementation of non-negative ratio is not good enough because this doesn't handle this empty list case. And of course we could fix this in a few different ways. We could widen the output type to option of big decimal, for example, or we could narrow down the input type to non-empty list of int, or of course we could also throw an exception, and that's probably the worst of the 3 options. So property-based testing is pretty good because it forces us to think about the general properties of our function, and it can help us reveal these gaps in the implementation. But it is not a guarantee for a strong test suite. So in this talk, as I said, I want to introduce an additional tool that we have available to basically test the quality of our tests, and that's mutation testing. So mutation testing is not another technique for writing tests, like property-based testing versus example-based testing. So you don't need to change anything about how you write your tests. You can use it with traditional example-based testing or with property-based testing. It doesn't really matter. So it's more something that has similar goals to code coverage. It wants to give an idea of how strong a test suite really is and where you have flaws in your test suite. So how does it work? Well, as I already said, it changes the code on the test, and then it runs your test suite against the modified code. And then we'll see if your tests actually care about the fact that the code on the test has been modified. So here's an example of a few examples of mutations that could be done. For example, we could have a mutation that replaces every greater than with a greater equals operator, or a greater than with a lower than, and so on and so on. And later in the talk you will see a few more mutations that are commonly implemented in mutation testing libraries. But this is just to give you an idea, and I will use one of them in the examples now. So what we want as mutations is code changes that are likely going to change the behavior of our function on the test. And if you think about it, this is exactly the opposite of the kinds of changes that we usually want when we refactor a function. Then we want to have the behavior stay exactly the same. So we have some tests for the function and they should not break when refactoring. So we have mutations, which a mutation is basically a strategy for how to change some piece of code in a source file. And when we apply such a mutation to a specific occurrence, for example, of the greater than operator, then this leads to a so-called mutant. So we never change multiple parts in the same source code file at once, or even in the same project, but every mutant is just a single individual change at one place. And each of these mutants has to be tested in isolation. So then we run our test suite against each of the mutants. And here we can see a test that fails when we run it against each of these mutants. So that's actually good, because apparently our test suite cares about the code under test, because the modified versions have actually led to test failures. And in the terminology of mutation testing, this means that the mutants have been detected. Some mutation testing tools also say that the mutant has been killed, but I prefer detected. And here's an example where the test suite is not quite as good. And in this case, mutant 1 actually is not detected. So the terminology often is that it has survived, because the test still succeeds for this mutant 1, where the greater equals has been modified to a greater than. So each mutant that has not been detected, of course, is a warning sign which tells us about a very concrete problem in our test suite. So now maybe you think you don't really need this because you're very experienced and you really know how to create a good test suite. And maybe you use property-based testing, so you already cover all the corner cases anyway. So why would you need a tool to test your tests? Well, in my opinion, experience doesn't prevent you really from being sloppy when you're in a hurry or from making mistakes. And regarding property-based testing, I think property-based testing and mutation testing, they really approach the same goal of high-quality software from two completely different angles. Because property-based testing, as we just saw, it can identify gaps in your implementation. And mutation testing reveals gaps in your tests. So it's actually complementary or orthogonal to each other. So mutation testing is just another tool like property-based testing, and I think if we use both of them together, then this is usually a pretty good idea. Okay, so you want mutation testing for your Scala projects now. But in Scala we were a bit late. In other languages there have been mutation testing tools for a few years. For example, there's Pit in Java, there's Mutant for Ruby, and there's a few others for other languages. But in Scala, until recently, there wasn't really anything that supports mutation testing. So more than 2 years ago, I had this vague idea that Scala Meta would be a great foundation for a Scala mutation testing library. And now I want to show you that this is really the case. So to understand what mutation testing really is and how it works, I'm going to show you how to build your own mutation testing tool with SPT and Scala Meta, which only takes 200 lines of code as a proof of concept, of course. But afterwards, I will show you the flaws of this proof of concept, and we'll look at an alternative that is still in development, but is already available. So I'm calling this SPT plugin Zalanda, based on a spell in the German tabletop role-playing game, The Dark Eye. Because in the 80s I used to have these spells which were based on silly rhymes, and Zalanda, Mutanda, Sei ein anderer is basically exactly what mutation testing is about. So the main ingredients are SPT and Scala Meta. And mutation testing consists of roughly of 4 steps. First we need to find all Scala source files under test. For each of these source files we want to yield all of the mutants for all the applicable mutations. And then for each mutant we want to run the whole test suite. And finally, when all of that is done, we want to analyze and log the results so that we can see which mutants were not detected and also in which place of our source code these mutants occurred. So these 4 steps translated to Scala code, basically this looks very much like the description from the previous slide. So this is a function. It gets this SPT managed logger and it gets an incantation which contains all the data needed for actually running the mutation tests. For each Scala source file it summons the mutants, and for each mutant it will run an experiment. And at the end we will analyze the results and log them. I will not go into detail for all of these steps, because some of them are pretty straightforward. But the interesting parts are finding the applicable mutations and creating mutants from them, and then running the test suite against each mutant. So, as I already said, we are using Scala Meta to find possible mutations and to create mutants. And Scala Meta is a library for reading, analyzing, or transforming Scala code. And one of the main components is that this tree type, which is a syntax tree representation of Scala code. And tree is pretty great because you can pattern match on it, you can traverse it, you can compare 2 trees with each other. So this is a pretty great tool for finding possible mutations and creating the mutants. There are a few methods for traversing a tree in Scala meta, but the one that we use is called collect. Collect expects a partial function from tree to t and gives you back a list of t's. So basically, you will collect all values of type t for the nodes in the tree for which the partial function is defined. So it's a bit similar to the collect function in the Scala collection library. Okay. Now, of course, we also need to have a way to define some mutations. And as I already said, we can think of mutations as a recipe for finding or getting from a source file to a list of mutants that can be applied in that source file. So I have defined a type alias for that. And in this example, I'm defining a mutation that changes the greater equals operator to either to a greater or to an equals operator. So for some operator or something else, so we can always give like a list of mutants, because there are usually multiple ways that we could change it. And as you can see here, we apply pattern matching on the tree in our partial function. So we are basically looking for application infix operator applications of this greater equals. Yeah, that's as simple as that. And what we get back is this list of mutants, where we simply copy this node and change the name greater equals to greater or to equals equal. So apart from that, of course, we need to give back the original source file in our mutant, because later we need to write the source file to our disk again, because this tree itself, of course, is just a very small thing in our source code, and we need to write back the modified source code. Okay. And of course, we have more than one mutation. So our spell book is a list of mutations. In this example, I just have 2 of them. But if this was not just a proof of concept, of course, there would be a lot more. And now we need a way to apply all of these mutations to our source file. So in this mutations object, I have a function which gets a source file and gives you a partial function from tree to list of mutant. So this basically satisfies the signature of the collect method. And what we do here is that we fold over the list of mutations so that we create a huge partial function where all of the individual partial functions are chained together. And then this can be passed to the collect method. Okay, so we also want to run the test suite against each mutant, of course, and we must have a way to identify the result. So I'm introducing an algebraic data type result. A mutant can either be detected, undetected, or there can be some sort of error. Now, when we want to run the test suite against the modified source code, there's a lot of SPT stuff going on here. Basically, for each mutant, we need to create an individual source directory. And in that directory, we will place a copy of all of our source files. But one of the source files will be modified at a single place. And then SPT, of course, needs to know that we are using not the normal target directory where the compiled classes are, but a new one for this specific mutant, because we are compiling the modified source files also to our own target directory. Okay, and then we run our test task with our modified SPT state with these changed settings, and then we need to map from the result of running the task to our result algebraic data type. So this is how we run a single experiment. So now let's have a look at what it looks like to use this mutation testing SPT task. So here we have again our familiar non-negative function, and we have a test suite that is not very good. So if we run Zalanda Mutanda in SPT, we would get this output. So we would see the total number of mutants and detected mutants, and each undetected mutant would be printed to the console. So we would see where the mutant is located and what the mutation was. And then, of course, we could navigate into our source code and also into our test suite and see what's the problem. So the position information here is also coming from Scala meta, because it really tries to preserve as much information as possible from our source code. Now, of course, this is a nice proof of concept, but it has a lot of weaknesses. One, of course, is a very limited set of mutations. The basic console reporting you just saw is also not really satisfactory. And there are definitely some performance problems. And I will talk about some of these problems a bit more. But I won't do it now. But first I want to introduce you to an alternative to this proof of concept. So I will actually show you what they did better in their not so completely naive implementation. So 1.5 years later or something like that, someone replied to my tweet and said, yes, it's really a good idea. Here's Striker for S. So Mugu has been working on this for quite a while. I also met him at Scala days. And Striker for S is already available today, but it's not really production ready yet. But I would definitely, I hope I can get you interested in it. So in Zalanda, I took some inspiration from its design, but I simplified a lot of things, of course. So Striker for S has its name because it's a Scala port of an already existing mutation testing library called Striker, which is a tool for JavaScript actually. And there are also other ports as far as I know. I think there's a .NET version. I think that might be all, so JavaScript.NET and Scala no. But it is available today, so we can use it in our Scala project, or at least try it out. So let's see what it can do for us. So first of all, the number of supported mutations is a lot bigger. We have Boolean literal, for example, to replace true with false, and the other way around. Conditional expressions, where some conditional expression is also replaced by true or by false. Equality operator is more or less what I had implemented in Zalanda. Logical operators are pretty straightforward, but so these 4 are more or less what you would expect from any mutation testing library from other languages. Method expressions is something that I have not seen a lot in other libraries, in other languages. And most of these replace a method from the Scala collections library with a different one, which is which you could sometimes make a mistake of using one instead of the others. For example, they replace an application of take with drop. And there's also, I think, exists can be replaced with for all and stuff like that. Then there's string literals, which can be replaced with an empty string. And those are the ones they have implemented for now. I think there are also ideas for some more Scala-specific mutations regarding pattern matching, for example. But they have not been implemented yet. Okay, so the other thing was the basic console reporting. Of course, Striker for us also can do console reporting, but they also have this really nice HTML report, which I think is far more usable, because mutation testing really should give you a lot of insights into the weak spots of your test suite. And this kind of report really helps a lot. So here you can see a mutant that has been detected. That's when we call this split method. And we have two others here which have not been detected. And here you can also see originally one of the mutants was that a false was replaced by a true. The other was that some string interpolation was replaced with an empty string. And in this example code, apparently my tests were not good enough that these have been detected. So this is pretty great in my opinion. What about performance? Well, we all know that the Scala compiler is not the fastest one. And for mutation testing, this is a big problem, because we usually create a lot of different mutants and each of them needs to be tested in isolation. So the naive way that I implemented, of course, was to compile the whole code base again and again for each single mutant. So we have these steps: mutate, compile, and test. Some mutation testing tools on the JVM do it differently. They modify the bytecode instead. And I think that can be potentially a lot faster than compiling Scala source code. But of course in Scala it's a bit tricky, because the Scala compiler, well, the bytecode that it produces, it can be incompatible between different Scala versions. So it would probably be a nightmare to maintain such a library for Scala. So what Striker for S is doing, they use a technique called mutation switching. So for some part of the code that is supposed to be modified, they don't do this naive direct replacement, but they actually instead they replace it with a pattern matching expression on an environment variable, active mutation. So at runtime they match on this value, but they can, at compile time, they can fuse multiple mutations together. And then for each mutation run, of course, the environment variable active mutation will have a different value. Okay, so how can we use it? Well, there is an SBT plugin. The current version is 0.601. And then there's an SBT task, which is simply called Striker. And there's also a configuration file. So you can't really configure this SBT plugin via SBT settings, but you have to use this striker4s.conf file, which uses the whole conf format. I think there's also a Maven plugin as far as I know. And in the configuration you can disable certain mutations altogether. You can also say that you don't want to have Striker modify all of the source files, but only some of them. Yeah, and one thing is that you can set a threshold for the detection rate, which would be similar to code coverage with a quality gate. You can make the build fail I wouldn't recommend using such an approach. I would also not recommend introducing mutation testing in your continuous integration pipeline. For very small projects, it only takes a few minutes, but for normally sized projects, it can take hours, or many hours for big projects. So I would probably run it locally on your own machine from time to time, or maybe once or twice a day in your pipeline, but as a separate job. Yeah, I would, as I already said, I wouldn't enforce a minimum detection rate, but I would just use it. I would use a report to get some insights into where your test suite can still be improved. Okay, so there are a few interesting challenges for building a mutation testing tool, and I will introduce some of them now. Some of them are actually Scala specific, and others are more general. So one of the things that hasn't been solved yet in Striker for us is that there are mutants that might not actually compile. For example, if you have a filter method, there's no guarantee in Scala that there's also a filter not method. It just happens to be the case on Scala collections, but anybody can define a filter method, of course. And this is even true for operators. So in Java, operators are really simple for mutation testing tools because they're built into the language and they only work on primitive types. So it's safe to assume that you can replace a greater than operator with a greater equals operator. But in Scala, again, anybody can define a method called greater than, and it doesn't mean that there's also a method called greater equals. And the problem here is, of course, that using just the Scala meta syntax tree, we have no type information available. So compile errors cause the whole mutation test run to fail currently, because there's currently no way of rolling back a mutation or a mutant and just ignoring it. Yeah, so because we only have syntax information, the mutations are a bit based on assumptions, of course. There are a few other issues. These are things that any mutation testing tool faces. You can introduce infinite loops by applying a mutation. Of course, there are some simple ways of preventing many of them. For example, you would never change the condition of a while loop to while true. But nevertheless, it can happen, of course. And some of the more mature libraries in other languages that would then have a timeout on running a test suite against a specific mutant. And if such a timeout occurs, it actually means that the mutant has been detected because the behavior has changed. Previously the test was green and now it's in an infinite loop. Then we have no native support for multi-module projects, but there is a workaround for that using the configuration file. So it is possible to use it with multi-module projects. You just have to do a little bit of configuration work. And performance, this is definitely better than my proof of concept. But what still happens is that for each mutant we run the complete test suite. And this could be improved if we were only running all the tests that are actually covering the mutated code. So this would require a mechanism to know if I change this function or something in this function, which test cases do I actually need to run, which test cases are covering this. There are a few ideas for improving Striker for us, but this is definitely not a roadmap. That's just ideas. from the Striker4S team. So one is to keep the test process alive instead of always starting a new JVM, and to ignore mutants without test coverage altogether. And another one is for each mutant to only run tests hitting the respective code, as I just said. And then the whole topic of robustness. There needs to be a mechanism for rolling back mutations that cause a compile error. And there is an idea to look at if semantic DB might help with relying less on assumptions and actually knowing which mutations are possible and which are not possible. Yeah, but regardless of whether you do example-based testing or property-based testing, I think mutation testing is a good tool to get an idea of the quality of your test suite. So I would invite you to have a look at Striker4S, or maybe even contribute to it, because it's actually pretty simple to do that. Yeah, and if you don't actually use Scala in your day job, maybe have a look at other mutation testing libraries like PIT. There are a few links here. There's this proof of concept. There are, of course, Striker4S, a blog article about how mutation switching works, because I've only shown it very briefly, and it's actually a bit more complex than what I've shown. And then Scala Meta if you want to play around with that. Okay, thank you, and if you have any questions, raise your hand or just shout. Thanks.
Any questions?
So there will be a lot of mutations all the time because you only change one occurrence to a greater than. Okay. So it's not like replace all with always this.
But it probably wouldn't make any sense to introduce many mutants at the same time, because then you don't know, based on the result, which one caused the changed behavior, right? Because they might interact. So you always need to make a single change and see what happens. And of course, the idea is not to introduce as many changes as possible and see what happens, but just to introduce behavior that is likely going to change, introduce changes that is likely going to change the behavior, right? But usually in a big project, then there will be a lot of mutants. Yeah. So I'm not sure if other mutation testing tools only actually use a subset of the possible mutants, but in Striker, we always use all the mutants that they found and run the tests for them. And I think some other tools might do it differently. Let's say randomly or however, only use a small subset of the possible mutants. Okay, another question?
Instead of changing the source code, wouldn't it be also a way to change the compiler? For example, the compiler plugin or something, and use this, because then you have all the type information and so on.
Well, this would be similar to using semantic DB, probably.
Yeah. Probably, yeah, but
yeah. I also think that with Scala 3 things will be maybe a bit better. And we have this intermediary format, which is a bit nicer to use than just the Scala syntax tree. Okay, other questions?
I want to thank Daniel again.
Thanks.